Welcome to the Green IC Research Group at the National University of Singapore. In this video, we are excited to share about a distributed on-chip scheme for continuous detection of laser voltage probing attacks against digital systems with full area coverage that exploits temperature sensing as detection method for the first time. This approach is standard cell-based, self-referenced, calibration-free, and design-agnostic for seamless adoption and design through automated digital design flows. Our approach reduces the area overhead to 58% in the very worst case, which is 2.5 times lower than prior art. We now welcome Hui, who will explain the circuit techniques and the architecture.
Hello, this is Hui. In our laser voltage probing attack method, we take advantage of the exponential dependence of subthreshold leakage on the temperature. This allows to differentiate the presence of a laser beam and hence temperature raised from the ordinary presence of local temperature hotspots, allowing reliable detection of LVP attacks. As shown by the measurements, the temperature induced by the laser used during an attack is much greater than the one generated by optics, allowing a wide detection margin. Temperature sensing allows lower area overhead than prior photosensing techniques, since the local temperature raise induced by the laser beam covers a radius within the chip area that is much larger than the optical laser beam spot size, making it easier to detect from temperature instead of conventional photosensing. In detail, detection is carried out by using a simple current mirror to compare the subthreshold leakage of different chip sites that can be exposed to the laser beam only individually in practical attacks. The thermal sensors are implemented in the form of off-mode transistors, generating a temperature-sensitive leakage current. The thermal sensors are then integrated into a standard cell design methodology, are pre-placed on chip according to a diamond-shaped pattern for maximum sensitivity and at a density that allows 100% area coverage. The proposed method is self-referenced, calibration-free, automated, and for design-agnostic adoption. Now Chiang will talk about the experimental results.
Hello, this is Chiang. State-of-the-art LVP attacks were executed on our 28nm test chip. The method easily differentiates local hotspots and the temperature raise due to the LVP laser spot. This is shown in these measurements, in which local temperature hotspots are intentionally induced by adjacent ring oscillators running at the high frequency of 8 GHz. This generates about 85-degree local temperature, which is much lower than the temperature induced by the laser beam of several hundreds of degrees Celsius. Compared to prior designs, this method uniquely enables always-on laser detection and full coverage even at the most challenging wavelengths above the bandgap, with full area coverage at a 58% area overhead. This corresponds to a 2.5x overhead reduction over optical sensing in previous designs at an equivalent level of security.
This test chip from our group demonstrates an on-chip laser voltage probing attack detection scheme that has much lower area overhead and hand cost compared to prior best-in-class designs. The proposed method is based on indirect temperature sensing instead of direct optical sensing of the laser beam. Its adoption in existing systems on chip and conventional standard cell design flows is facilitated by its self-referenced and design-agnostic nature. Overall, this technique pushes physical security against laser voltage probing attacks to the next level, making it much less expensive and hence more widely adoptable in next-generation systems on chip. Thank you for watching. Feel free to explore more in our Green IC website.